As we continue with Laplace, we're going to investigate how Laplace transformation can be used to solve certain types of equations. Now, if we do a Laplace, we end up with guys that look something like this. So the inverse Laplace brings them back. Now, like derivatives, doing a Laplace allows us to just do the rules and come up with the answer. With the inverse Laplace, it's like integrals. We have to match exactly what's here in order to do the inverse Laplace. So these are some rules you need to look at and be able to understand so that we can use them. Because what we're going to do is we're going to start with an ordinary differential equation. We are going to then try to solve for find the solution, y of t, that satisfies with the initial conditions given. And what we're going to do is we're going to apply Laplace transformation to the function. Once we apply the Laplace, we will now have a function in S, an algebraic equation. Right? Simplify it, solve for y of S. Then we will use the transformation for y of S by applying the inverse transformations, and we'll be back to y of t. Now, in order to do that, we need to understand the one extra part is what is the Laplace due to a derivative, right? And so Laplace works on the nth derivative. It's going to make it s to the n, a function of s, minus s to the n minus 1, the value of the function at 0. So that's initial value need to be given, right? And then s of n minus 2, the function's derivative value, and so forth. And we're not going to go very far with that. We'll start with limited ones. But we first need to make sure we understand how to do the inverse Laplace. So again, here are the rules for the inverse Laplace. So, inverse Laplace of 1 over s to the 5th. Right, so we look up here, and all right, that's s to the 1st. Oh, here's s to a power bigger than 1. But notice the numerator has to be n factorial. So to get 1 over s to the 5th, I need, n in this case is 4, s to the 5th, n plus 1. So n is 4. So I need 4 factorial in the numerator to match this. I need 4 factorial in the numerator to match this. And as long as I undo it, 1 over 4 factorial, now I have 4 factorial s to the 5th. Okay, n factorial s to the n plus 1. What's that equal? It equals t to the n. So that'll be t to the 4th. And then we have the 1 over 4 factorial, so it's 1 over 24 t to the 4th. 1 plus s squared, 1 over s squared plus 7. Inverse Laplace, all right? S squared plus 7. Well, we look, and all right. Here's one that is s squared plus a number squared with a number on top. And that's what we have. We have a number on top. Here's s squared plus a number squared, but it has a variable on top. So this is a number. So it's this one. Well, this then is the square root of 7 squared. And so I need to have k on top. So I need a square root of 7 on top so that this matches that. Well, I got to multiply by 1 over the square root of 7. So now this, the inverse Laplace, has a sine of kt, and then 1 over the square root of 2. So that's the process, right? And if we have more difficult ones, we have to be able to do the process on them also. Here we go. So if we want to do the Laplace of minus 2s plus 6 over s squared plus 4, Well, I got to rewrite it, just like we have to do with integrals. Got to rewrite. So it's going to be minus 2s over s squared plus 4. And it's going to be 6 over s squared plus 4. So we have two formulas that involve s squared plus k squared. One has a variable on top. So to make this work, I've got to factor out a 2. And now I've got s over s squared plus 4. That fits one of the rules. That fits one of the rules. The cosine rule. Go look at it. Now this one I need s squared plus 4. K is 2, so I need a 2 on top. Well, I've got a 6, so if I pull out a 3, I now have a 2 on top. And now this is going to be 3 sine of 2t. It's how we do it. How we do it. Sometimes it's a little more difficult than that. And here's another example. I'll let you look through this example, and then I will go back and do a pin cast so that you have the whole example. Okay, how does that help us do derivatives? Right? How does that help us do derivatives? Well, we first need to figure out, if we're going to do a Laplace, what does Laplace do to the first derivative? Well, it's going to make it s times a function of s minus f of 0. So we have to know f of 0. Initial condition has to be given. Or if it's a second derivative, it's s squared f of s minus s times f of 0 minus f prime of 0. It was the third derivative, be s cubed, the function of s, minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. And in general, it looks like that. So how does that help us to find, right? Well, you've seen this already if you looked at it, but you're going to start with a known function. You're going to apply Laplace, and now we're going to have a function in s. They keep going back and forth between y of s and f of s. It's a function of s. I don't care how you write it. Since this is y of t, many times they write it as big Y of s. Then you solve that for big Y of s. You then do an inverse Laplace, and you will have your solution. So inverse Laplace, and you will have your solution. Right? So how does that work? Now here's one. dy dt. So we needed to do a Laplace on that. Then 3y, we need to do Laplace on that, equals 13. We need to do a Laplace on that. Okay? So the first derivative is s, function of s minus fy0. Well, y0 was given as 6. So s, function of s minus 6. So there's our first piece. It's that. 3 Laplace on y becomes 3 big Y of s. And Laplace on a sine, right, that's going to be the denominator of s squared plus 4, right, over 2, and we have a 13, so 26. So this is what we get. So now there's the Laplace. Step 1. Take your function, your differential equation, apply Laplace, and now you've transformed it. Now solve that for y of s. So here's y of s. So we get s minus 3, or s plus 3 times y of s. That's not an s, so we're going to subtract it, or add the opposite to both sides. And then if we want to, leave that piece up there first, okay? So now we've got this, and we want to solve for y of s. We got to divide by s plus 3, so it's going to be 6 over s plus 3, and 26 s squared plus 4 over s plus 3. So we're going to get that result. And we then, common denominator, s plus 3 and s squared plus 4. So multiply this by s squared plus 4, so that's 6s squared plus 24 plus your 26, so it's 6s squared plus 50. So now we have to take and break this up, partial fractions. And so we've got a over s plus 3 and bs plus c over x squared plus 3. And if you do all of that, right, you end up down here. A turns out to be 8, b is minus 2, and c is 6. So now, y of s, we now need to do an inverse Laplace. So the inverse Laplace of y of s is y of t. And we have 8s plus 3. Well, 1 over s plus 3, there's a rule. That's in e. So this is going to be 8e to the minus 3t. Look at the inverse Laplace rule. Then minus 2s over s squared plus 4. We already looked at that. That's minus 2. S over s squared plus 4, that's cosine. So it's minus 2 cosine of 2t. And then 6 over, well, we needed s squared plus 4, so we needed a 2 up top. So that's 3 sine of 2t. And we have solved the differential equation. We have solved the differential equation. There are a couple of videos on that. I'll do a pen cast on this problem going step by step. And we now have the technique for solving differential equations using Laplace. Technique solving differential equations using Laplace, following these steps.